Okay, hello everyone. In Unit 5, we have three topics. One is laminar flow and viscous effects. Next is flow past immersed bodies. And the third one is introduction to compressible flow. So, I have made two videos on laminar flow and viscous effects, one for theory, another for problem. Then one video on flow past immersed bodies, where we will discuss lift and drag force. And third one is the introduction to compressible flow, where we will discuss about the Mach number, sonic and subsonic velocity. So, first we will understand what is the relation for laminar flow and viscous effects. So, the flow is classified as laminar and viscous based on a dimensionless number called as Reynolds number. This already we have studied in fluid kinematics. This Reynolds number Re is given by rho Vd by mu, that is the ratio of inertia force to viscous force. So, for a given fixed diameter pipe, d is constant, and for a given fluid, rho and mu are constant. So, finally, Reynolds number is a function of velocity. So, it is obvious that when velocity is low, that is when the Reynolds number is less than 2000, the flow can be assumed to be laminar, that is flowing in terms of plates as shown for the flow between a parallel plate, or if the flow is in a circular pipe, the flow can be imagined to be flowing in circular laminae as shown in the diagram. And if you conduct an experiment where the flow starts or the velocity starts increasing, then there will be a particular Reynolds number at which the flow changes from laminar to viscous, or if you do the experiment in a reverse way, the flow may be changing from viscous to laminar. So, that is called as a critical Reynolds number, the Reynolds number at which the flow changes from L to T or T to L, that is what is written there. And similarly, based on that experiment, the number can be classified from lower critical Reynolds number and or upper critical Reynolds number, whether the flow is from laminar to turbulent or turbulent to laminar. So, there is a small concept about that. Our main objective in this topic is to understand the shear stress distribution, the velocity distribution, the ratio of maximum to average velocity, as well as the pressure drop per unit length when the flow is strictly laminar. That is, if the flow is taking place in a pipe and if the flow is assumed to be laminar, then our objective is what is the shear stress plot, that is from one end of the pipe to the other end, or from one corner of pipe to the other corner in a cross section, what is the shear stress distribution, whether it is maximum at the center, whether it is minimum at the center. That is what we are trying to understand. Similarly, how the velocity varies and what is the ratio of maximum to average velocity, and finally, for a given length, how much pressure will be dropped. This is what we are going to discuss here. So, this is also called as the Hagen-Poiseuille's equation. So, we have please go through the diagram. Here a cylindrical shaped fluid element is considered, where the length between the two ends is delta x. P1 is the pressure at one end, P2 is P plus delta P is the pressure acting at the other end, and the resistance to this flow is denoted by the symbol tau. So, tau is the shear force. So, as indicated in the bracket, we are going to plot shear stress distribution, velocity, ratio of maximum to average, and the pressure drop. In the side, you can see that the fluid is having a cylindrical shape. The distance between the center of pipe to the fluid element that we have considered is small r, and the maximum distance or maximum radius of the pipe is capital R. The left side plot is one for shear stress, one for velocity, that we will understand only after we derive the relation. So, our first objective here is to derive the shear stress distribution. So, to derive the shear stress distribution, we have to consider the fluid element to be in equilibrium. So, when I consider the equilibrium of this fluid element, we will get P1 into dA or P1 into A, where A is the area of cross section of that fluid element, not the complete area, minus P plus delta P into dA minus tau into 2 pi r into dx must be equal to 0. Tau into 2 pi r dx indicates the total surface area of that fluid element, which is 2 pi r dx, and tau is the shear force. So, when you simplify, you will get tau is equal to minus dp by dx into small r by 2. So, here you can see that shear stress is directly a function of radius, and delta p by delta x indicates that it is a pressure gradient. The negative sign indicates the pressure decreases with the length. The other observation from this equation is tau varies directly as r. So, if I put the limits of r, when r is 0, we can see that shear stress is 0, and when small r is capital R, the shear stress becomes maximum. So, tau max is minus delta p by dx into capital R by 2. So, here one note is, do not separate the minus sign from delta p by delta x, always the pressure gradient is negative. So, let us keep that minus delta p by delta x into a bracket everywhere. So, that is what is the explanation written in the third page. Tau varies as r, tau max is minus delta p by delta x to r by 2. Next, to determine the velocity distribution, we can use the Newton's law of viscosity, which is tau is equal to mu into du by dy. But in the derivation of Newton's law, dy was the distance of the laminae from a fixed plate, but here that laminae is at a distance of capital R minus small r. You can see from the diagram. So if y is r minus r, dy is minus dr, because capital R is a constant. So if I substitute that, then I will get the equation minus delta p by delta x into r by 2, which you have just derived, must be equal to minus mu into du by dr. But here our objective is to get an equation for velocity. So when I separate the terms for velocity and integrate, I get u is equal to minus 1 by 2 mu delta p by delta x into r square by 2 plus k, where k is an integration constant. Now this value of k can be obtained from boundary conditions. And what are the boundary conditions here? When r is equal to capital R, that is at the periphery of, or at the point where the fluid is in contact with the pipe, you can see that velocity is 0. Therefore, if we substitute that, we will get the value of k. K is 1 by 4 mu minus delta pi by delta x into capital R square. So if I substitute the value of k in the equation, we get u is equal to 1 by 4 mu minus delta pi by delta x into r square minus small r square. So if I take capital R square outside, it becomes an equation as 1 minus r by r whole square, which is an equation of parabola. Therefore, the plot is as shown. It is plotted in the first diagram. It will be a parabolic shape, and at the center, when you substitute the value of small r as 0, you will get the maximum velocity. That is, when r is 0, we get u max is 1 by 4 mu minus delta p by delta x into capital R square. So you can see the plot, but in this plot you can see that velocity is maximum at the center and 0 at the periphery. But what is the average velocity? Whenever we say that fluid is flowing at 8 meters per second, we are talking about the average velocity. So next observation will be, what is the ratio of maximum to average velocity? So to find this, we will use the same equation that we have derived for velocity. We have small u is equal to so and so. When I substitute small r as 0, I will get u max. Now to get the average velocity, we have to find the total discharge to the pipe divided by the cross section area of the pipe, which is pi r square. Now again, to find the discharge, we have to find the discharge through an elementary strip, then integrate it over the limits. So I have written q is integration of dq, where dq is again area of flow through the strip into velocity through the strip, that is small dq. Now this strip, how to find the area of the strip? This strip, when it is opened, it is having a length of 2 pi r and thickness as dr. So the area of the strip is 2 pi r dr. So dq is 2 pi r dr into velocity at small radius r, which is already derived, that is 1 by 4 mu into minus dou p by dx into r square minus r square. So if you substitute these two equations and simplify and integrate it, you are going to get q as pi by 8 mu minus delta p by delta x into r raised to 4. So you have to carefully derive this by simplifying all the terms. Now we have the total discharge through the pipe available, and now we know that total cross section area of the pipe is A is equal to pi r square. So again, using continuity equation, u bar, which is the average velocity, is q by A. So when I substitute that, we are going to get u bar as 1 by 8 mu minus delta p by delta x into capital R square. But u max is already 1 by 4 mu minus delta p by delta x into r square. When you substitute these values, you will get u max by u bar as exactly equal to 2.0. That means the maximum velocity is always twice the average velocity of fluid flowing through the cross section of the pipe for laminar flow through a circular pipe. So here the hint I have written for deriving the above equation is, for tau equation we use summation f equal to 0. For getting the equation for velocity, use Newton's law and combine this with shear stress distribution. For getting u bar, use continuity equation q is equal to u bar into A. And for getting delta p, that is the pressure drop per unit length, again we will use u bar equation as shown in the next page. So here in the last part of this derivation, our objective is to find the pressure drop per unit length of the pipe. Again, the flow is considered between two sections 1 and 2. From a fixed periphery, let that section 1 is at a distance of x1, section 2 is at a distance of x2. So L is x2 minus x1. Now instead of deriving it separately, we can use already derived equation, that is average velocity is the velocity which we always consider. So let us use that. So we have u bar is 1 by 8 mu minus delta p by delta x into r square. Now here the main parameter to be derived is delta p by delta x, we want to expand. So when I separate the terms, I will get minus delta p by delta x is equal to 8 mu u bar by r square, or delta p is 8 mu u bar by r square into delta x. So if I separate it and integrate between the limits 1 and 2, I get minus into bracket p2 minus p1 into so and so. If I bring that minus term inside, it becomes p1 minus p2. But what is P1 minus P2? It is nothing but the pressure drop. So, delta P is 8 mu u bar L by r square, or in terms of diameter it becomes 32 mu u bar L by d square. So, this is also known as Hagen-Poiseuille's equation. But we already know that the head loss per unit length HF is P1 minus P2 by rho g. We are using it from since from unit 1. So, delta, if I take that equation and substitute here, or if I divide delta P by rho g, it becomes 32 mu u bar L by rho g d square. So, this derivation is also known as Hagen-Poiseuille's equation. So, when you are deriving this, so if you are asked to derive all these 4 equations for 12 marks, you have to start from the initial part, then derive tau, u bar, u max, and complete it up to here. Or if only Hagen-Poiseuille equation is asked for maybe 4 or 5 marks, then directly you can assume u bar equation and directly derive it. So, your solution depends on the amount of or the weightage given to that, that is in terms of the marks. So, I will quickly go through all these 4 derivations since we have some more time, because the maximum limit for each video is 15 minutes. So, we have considered the flow across a pipeline. A fluid element of cylindrical shape is concerned. P1 and P plus delta P are the pressure at two ends. Tau is the shear stress acting around the. So, here this lamina is experiencing shear stress because of the lamina which is above it, and also there may be a lamina which is inside it, but at any arbitrary distance small r we are considering this lamina. Now, to get the equation for shear stress, you just take the summation of all the force equal to 0. So, it is very simple, P dA minus P plus delta P dA and all minus tau into 2 pi r dx. This is very important. The surface area of the cylinder is 2 pi r into delta x, where delta x is the length of the cylinder. So, we get the equation for shear stress. Next, use the Newton's law of viscosity as tau is equal to mu du by dy. So, convert the dy in terms of r. So, y is nothing but capital R minus small r here. The strip is at a distance of capital R minus small r. So, when you derive that in terms of r and equate it to the earlier derived equation, we get the equation for u, that is u is 1 by 4 mu minus delta p by delta x into r square minus r square, which is having the shape of parabola. Please remember, the constant k here is obtained by boundary condition that at small r is equal to capital R, u is equal to 0. This we are sure, but do not use the boundary equation here as when r is 0, u is u max. We do not know this unless we derive this. So, the only boundary condition we can use is when small r is equal to capital R, at the pipe we have u is equal to 0. So, when you substitute, you will get the equation for u. Now, when you substitute small r is equal to 0, you will get u max. Then to find u bar, use the continuity equation that discharge is velocity into area. So, when I want to find discharge, again discharge can be found out by integrating the discharge over a strip. Now, for that strip, when it is expanded, that circular strip, we already know the area of the strip, and velocity at small radius r is already derived. So, multiply these two equations, get an equation for dq, integrate it over the limits 0 to r, you will get the equation for q, divide q by area of pipe, you will get the equation for u bar. Then you can prove that u max by u bar is 2.0. Now, to get the pressure drop per unit length, use the u bar equation, substitute the limits as x1 and x2 in terms of L, and finally you will get the equation for the Hagen, that is delta P, which is also known as Hagen-Poiseuille's equation. So, in the next video, we have solved few problems related to this concept.